In this video, let's talk about analog to digital conversion. So here's the outline of this video. First, we have analog versus digital, then the analog to digital conversion process with steps like sampling, quantization, and coding. Finally, we will look at an ADC in Simulink. What does it mean to convert an analog signal into a digital signal? First, let's look at the difference between an analog signal and a digital signal. An analog signal is continuous in time and continuous in value, like seen on this figure on the left. This means that for any point in time, the voltage value of the signal is known or is defined. Digital signals, on the other hand, are discrete in time and quantized in value. This means that our digital signal is only defined for equally spaced points in time. For the other instances in time, the value is undefined. Like seen in this figure on the right, the value of the signal is only defined on these instances, and everywhere else, the value is unknown. Quantized in value means that there is a finite set of values that a digitized version of our signal can take. We will discuss this more later. The analog to digital conversion process can be simplified into three basic steps. However, in actual hardware implementations, this may happen simultaneously. First is the sampling step. In this step, we convert the signal from a continuous time and continuous valued signal, seen on the left, into a discrete time and continuous valued signal, like seen on the right. We achieve this by sampling the signal in constant intervals. The important difference here is in the discrete time signal, the values are only known for the sampling instances. For example, here, etc. And for everywhere else, the value is unknown. The next step is the quantization step. From a discrete time, continuous valued signal, we convert it into a discrete time and quantized value signal. To put it simply, we round off the values into the nearest quantization levels of the quantizer. The quantizer can be defined using three characteristics: its resolution, minimum input value, and maximum output value. Basically, the quantizer maps the input values into a finite set of values. In our case, we want the input values to be as close to the output values as possible. For our quantizer, how do we choose the finite set of output values and how do we map the input values into the output values, considering that we want our output values to be as close as possible to our input values? First, we make the assumption that our input signal is uniformly distributed. With this assumption, in order to ensure that we minimize the distance between the input value and the output value, we must also choose a set of outputs that is uniformly distributed across the input range, like in this figure. Each of these steps is a quantization level, and the difference between neighboring quantization levels is called the quantization step. Now that we know how we can distribute the quantization levels across our input range, how many quantization levels should we have? The number of quantization levels L is dictated by the resolution of the quantizer N. These two values are related by this equation. L equals 2 raised to N. Now let's try to compare two quantizers with different resolutions. The quantizer on the left has a resolution of 3 bits, and the quantizer on the right has a resolution of 8 bits. As we can see here, having a higher resolution allows us to track our input signal more closely compared to having a lower resolution. This means that as we increase our resolution, the difference between the input and the output of the quantizer becomes smaller and smaller. Thus, our digitized signal becomes more similar to our analog signal. The last step of the analog to digital conversion process is encoding. Digital circuits can only process signals in binary format, like ones and zeros. Thus, we also need to represent our signal in binary. We do this by assigning a binary number to each of the output of the quantizer. The simplest way we can do this is to start from 0 for the smallest quantization level and count up from there. This means that we need at least n bits for our encoder. We can model an ideal ADC in Simulink using these blocks. So the zero order hold block serves as the sampler. Then we have a quantizer block and a saturation block. In this model, we did not include the encoder. We can control the specifications of our ADC by changing the parameters of these blocks. For the sampler, we can adjust our sampling rates by changing this. This is the sampling period. And for the quantizer, we can change the quantization interval by changing this parameter. The saturation block is necessary to specify the upper limit and the lower limit of our input range. So if we run our simulation and look at the scope, this is a sample output of our simulation. That is the end of this video. Bye!